Okay, for this video, it is for module 4. I think I cannot cover all, which is there are too many here. Maybe I'm going to like separate with to be 2 video. So let's try to look into how we can do it. Okay, basically in our module 4, it is under instruction set architecture, ISA. What we're going to cover here, of course, we have introduction and summary, and in between we're going to learn on machine instruction characteristic, type of operand, addressing mode, instruction format. And for last time we have module 3 and today is our module 4. These 2 module is going to cover in your task 2. So I hope that we can try to finish as soon as possible. Okay, in introduction, we're going to look into several, which is hierarchy of computer language, general concept of our system. Nowadays, we are using x86, 64 bits, processor architecture, design decision for instruction set, and lastly the ISA level. So the hierarchy also we're going to look into. So here is the part that I really hate, which is I need to read. One boundary where your computer, the computer design and the computer programmer can view the same machines is the machine instruction set. So implementing the processor is a task that in large part involves implementing the machine instruction set. So the user who chooses to program in the machine language, which is our assembly language, of course, become aware of the register and memory structure, the type of data directly supported by the machines, and lastly, the functionings of the ALU itself. So, in this in this topic, you will like normally ask yourself what is basically assembly language, and of course you will ask yourself why you need to learn assembly language. Is it important for you or not, right? Are you going to use in your daily activities or not? So here, the purpose of you learn assembly language, I already informed you last time, which is this is a very basic language, and of course from the basic you can catch up or easily for you to understand other type of higher level language. And then what is machine language? It is basically the assembly language. How is assembly related to machine language? What is assembler? How is assembler? So all of these are questions that you can answer after you go through your module 4. So here is your the hierarchy of our computer language. You can see this is hardware, which is like maybe your computer, micro program control, and there will be a machine's language here. You can see machine language, and assembly language is basically will convert to your machine's language, which is similar. And you can see now here is your high level language, your C programming, your Java, your Python, a lot of other higher level language. Later on you will see the hierarchy, how you basically can convert your C programming, your Java to your assembly language. Then from assembly language, you can interact to your computer, which is using your machine's language. So which one is your machine independent, which is your machine specific? So this all here up, which is high level language, and lower is your low level language. Okay, wait. Okay, we continue. Okay. Now we're going to see the relations between our assembly and also machine's language. You can see here, what is machine's language, what is assembly language. So machine's language is a native to a processor, executed directly by their hardware. Instruction consists of 101010, which is generated from your assembly language, of course. That's why in you need to understand the binary concept. Last time we learned on the numbering system, right? Assembly language is a programming language that use symbolic name to represent your operation, register, memory, location, which is slightly higher level language, which is slightly only, but it is not too high. Not high level language. Readability of instruction is better than your machine's language, because if you look into machine language, it is all 011010. Why I cannot write here? 1100, whatever. This one we can't to understand. We are human. We can't to understand the codes. That's why this is basically converted from our assembly language, which is in terms of readables, human readables. We understand what are written there. One-to-one correspondent with our machine's language instructions. Okay, you can see here, compiler and assembler. When we have higher level language, let's say C programming lah, the always chosen, or maybe because this one is like much more easier rather than if you compare to C Java, Python, right? So if let's say you have C, when you write a C programming, how you can basically your computer know what you are written there. So your machines, your laptop, your computer will know by using your converter, which is called as a compiler. So you need to have a compiler, then it can be converted to your machine's language, whereby it is used for your laptop, for your computer to understand, okay, to read your instruction. While our higher level language or C programming and etc. can be also converted by using our compiler to the assembly language. But our assembly language can directly go to the machine language by using the assembler. So this is the correlation. You need assembler to assemble your assembly language to machine learning. While for higher level language, if you want to convert to assembly language or even for the machine's language, you need a compiler. Okay, what is compiler? What is assembler? Compiler translate higher level program to machine code. Either it directly, you can see, either it is directly or indirectly via assembly language. Okay, so you can have partial and also full. While for assembler, it's going to translate assembly to the machine's language. Okay, so you know already what is the compiler, what is the assembler. Now, for high level language, what is the advantage and what is the advantages? Okay, advantage for the high level language Java, Python, it is faster. And if let's say you are using like assembly language, okay, you have 3 paragraph, let's say, but in Java you just having 1 paragraph or 1 sentences. It is represent as 3 assembly language line. So that is it says that it is much faster because just read 1 line, occupy 3 line is assembler, which is called as a fewer instruction to code. Second, what else? Okay, you can see here, we have program maintenance is easier, which is same also reason acceptable because it's have a fewer code. So let's say we can just maintain only 1 line, while this one we need to like change for 3 lines. So that is the reason. And one more thing, the advantages is program are portable. What is portable? Which is it contain a few machine dependent detail, which is you can basically change from C programming to Java, can be used with little or sometimes no modifications on different machines. And compiler translate to the target machine language. But if you compare to the assembly language, it is not portable. So different machines you need to like mostly major modifications are needed. Why assembly language? What is the advantages if compared to the C programming, which is high level language? Okay, assembly language, which is it is accessible to your system hardware, which useful for implementing a system software, useful for a small embedded system application. And for the space and time efficient, which is understanding source of program inefficiency, tuning program performance and writing compact codes. So this is advantages of your assembly language. So you need to know both. Oh, there is another, under our assembly language, written assembly program give the computer designer the needs on deep understanding. So that's why you need to learn on assembly language first, because it's you're going to go in depth for the understanding, then you can go for higher. Another one is to able to write compiler for HLS. We need to be expert with a machine language. Assembly programming provide this experience. Okay, now we are looking at the general concept. For normally our computers, it is really rare to find their X32, which is 32-bit currently. Normally we use X86, but yeah, still there is a few a computer or a system still using the old versions of processor. So for X86 processor architecture, for X86 processor family, we're going to learn in our general concept here. Assembly language is a great tool for learning how a computer works, and it requires you to have a working knowledge of computer hardware. The concept in this section will help to understand the assembly language code that we written. Okay, this is a block diagram of a microcomputer. If you have a microcomputer, you're going to have, of course, going to have CPU. This is CPU, which is content, ALU, CU, and also your register. This one is register. So sometimes you also having a clock there. And you're going to have a bar system. You can see you have a bar system. And you have a memory and input output device. That's why last time you can see the basic things that you needed is input, output. Of course, this one is output, this one is input, and you're going to have a process, which is processor, and you have a storage, which is this one, your memory. Okay, the definitions on what is basically clock. Clock is synchronized the internal CPU operation. While CU, I think this both two you already know is already yet right. CU, ALU, and I think it's very easy for you to understand at this part. Okay, this one you already learned in digital logic subject on the clock. When you see this signal, of course you will like, okay, this is a clock. Because normally you often meet this in your digital logic last time. Like this one is one cycle. This is one cycle. This is one cycle. So you have several cycle in your clock, which is synchronized all CPU and bus operation. That is the function, one of the function. And it can be also the machine's clock cycle, which is it goes to measure time of a single operation. And lastly, clock is used to trigger event. Whether last time if you still remember, positive clock, negative clock. If positive clock, at this part they're going to trigger your output and also your input result. Maybe it is a negative clock. Okay, at this part, then you're going to trigger. So it is also a trigger event. Okay, this is the simple architecture or block diagram for your CPU. Inside of this, although last time you already know your CPU are content of ALU, register, control unit. Last time you see this part only, right? But inside the CPU, basically there's a lot, including a system bus there, which is connected. All your CPU are connected to your memory. No need for you to memorize all the detail like this figure, but later on, after this, you're going to learn what is fetch, decode, fetch operand, execute, store output, which is related to all the connection there. This one is example of memory read cycle. When you have a clock there, you can see you have a clock. of course, this is one clock cycle, another cycle, another cycle, another cycle. You can see here, there, if you have the ADDR address, your data. So this is how your connectivity between each other. This is using your data bus. Okay, now you can see here. Multiple machine cycle are required when reading from memory because its respond much more slower than your CPU. So you can see here, refer to this figure. You have a clock 1, 2, 3, and 4. See, the steps are for the cycle 1, address placed on your address bus ADDR. So this is normally the step by step before you going to because you're going to read inside your memory in your CPU. So you're going to put first your address on the ADDR, your address bus. Second cycle, which is your red line, is going to be set second. Okay, now you can see your RD is going to set as a 0. This one is placed your ADDR, address to your ADDR. Third, CPU wait 1 cycle for memory to respond. So nothing will happen here basically, but you're going to see it's going to wait for a memory to respond. Cycle 4, RD goes 1 indicate that data is on the data bus. It's going to be 1, indicate that the data is already there. This one, it's wait for 1 cycle. After that, it's going to see, yeah, the data is already there. It need to wait first. Then it's going to have data. So this is the flow for the multiple machine cycle. Require a reading from a memory. How program run? Okay, if basically you open your words, you open your PDF, you open your PowerPoint, whatever program that you have in your laptop, basically what is happening inside your computer. So let's say you opening, here is your text editor. Let's say you have a text editor you want to open, so you're going to open from your source file. And then step 2 is going to assembler, which is a assembling process happen there. And the assembler will divide it into object file and listing file of your text editor. But normally we can't to see all the listing file there. We just see the text later on after the upright. And it's going to process the linking. So that's why link library will involve here. And running a program later on, you're going to execute the file. It's open your file, your text file, going to execute. But of course, it's going to take process, maybe 0.0 microsecond. Of course, we can't to see basically. But this is the process. And there is a map file. Steps 4, your OS operating system will load your executable file there, and that's why you can see your output. Okay, so this is a step by step. What is basically happen? Maybe you open your a PowerPoint. And then this is a similar step. There open object file. There is also a listing file waiting there. And then the link library will do the linking, and it's going to open your executable file, and it will save the map file there first. And after your OS load your executable file for your PPT, it's going to open and pop up. Sometimes if you can see, if your computer is slow, then you can loading first before you open. That is because all of this process until then you can see the final output. Okay, what is listing file here? What is a map file here? Now we're going to look into one by one. Listing file, it is used to see how your program is compiled. So what is the inside things here? It is content of your source code, addresses, object code, or your mission's language, segment name, symbol, which is including the variables, procedures, and contents. So normally you're going to save it as like your name and dot lst. So this is an example. The codes that you can see, that dot list there. But normally we can't to see this all, right? When we open our operations. 32-bit addresses indicate the relative byte distance of each segment from the beginning of the program code. This one is the addresses. So this is an example of your listing file here. What else? This one in your template that you used last time. This one is content no executable instruction, which is directive. Assembly language instruction is each of 5 bytes long. The hexadecimal value in the second column here, such as B8 and then 001000 are actually instruction bytes. So here is the things that under your dot list. So what is your dot list inside here? You can see now, right? So what is the map file? Map file are informations about each program segment. Starting address, ending address, size, and segment type. So this is example of your map file. You can see you have the start, stop, length, name, class there. So just example, you need to know what is the segments inside your map file there. Okay, next you can see the design decision for the instruction set. When a computer architecture is in the design phase, the instruction set format must be determined before many other decisions can be made. So it's going to be determined first. Selecting this format is often quite difficult because instruction set must match the architecture before you can proceed. If the architecture is well designed, then it can last 4 decades. So this is the ISA level, the last sections under your introductions. What is ISA level? ISA, Instruction Set Architecture. So this is your ISA level. Is defined as interface. So you need to have that interface between your hardware and also your compiler, which is your high level language. It is the language that both them understand. So high level language is defined as an interface between the compiler. So let's say you have C program. C programming you compile to the ISA program, which is this all up here is software. Or maybe you have the 1490 program. You compile to ISA program first. Then the ISA will execute by the program, the micro program or hardwire. So instruction set architecture ISA are measured by several different factors, including the amount of space of program required, the complexity of the instruction set, the length of the instruction, and lastly, the total number of the instructions. So this is the things that make ISA different between each other. Now that is the one that I said. Lastly, ISA is the last subtopic for you under introduction. So it is just introduction. It's quite boring, of course. But if you go for like a technical, you play around with Visual Studio, it's much more interesting. Okay, now we have the machine instruction characteristic, which is elements of a machine instruction, instruction representation, instruction type, number of addresses, instruction set design. Elements of machine's instruction. The operations of processor is determined by the instruction it executes, refer as your machine's instruction or a machine's computer instructions. The collections of different instructions that a processor can execute is referred to processor instruction set, which is each of your instruction here must contain the information required by your processor before you can execute it. Okay, this table normally you found it in your chapter 1, module 1, the elements of machine instruction. So here you have operating code. Sometimes normally we like just say it opcode. Okay. Opcode is your operation code. And what is the functions? What is the functions of your machine's code? Opcode. What is the functions of opcode? It is a specific for operations to be performed. Your binary code, whether it's like you move, your additions, which is add, your subtraction, which is sub, your what else? Your multiplication, which is MUL. There is a lot others. Move, sub, multiplication, divisions also. So all of these are referring as your opcode. And your source operand A source operand reference. The operations may involve one or more source operand, that is, operands that are input for the operation. Result operand refer. The operand may produce a result, which is destination. Next instructions reference. This tells the processor where to fetch the next instruction after the executions of this instruction completed. So you need to remember the table here. Okay, here is example. Portions of an assembly language. So if you see here, sometimes you don't know, okay, this one is smooth. I know this is smooth, but what we call it as a opcode. Just now we learn, right? This one, opcode, the example is what? Okay. Now, all of these, the things that instruct you, is can call as a opcode, operation code. What else? Oh, oops. I forgot. My battery is low now. I need to charge. Okay. Now you can see. Next is source operand. Last time we already look into, which is here will be your destination. Here will be your source. So it's called as source operand. Next is your destination operand. And sometimes we can see this is not called as source operand, but instead you were given with the direct value, we call as immediate value there. This one is source because this is register. From this register, we're going to put inside. From this total, you will declare something right on top. From this total there, you're going to move to your AX. So when you have like opcode, which is add, you're going to have 2 here, which is immediate value. You're going to add with your 2, and etc. So this is what you need to know: opcode, source operand, destinations operand, immediate value, which is under source operand also. Source and result operand, which is destination, can be in one of 4 areas. First is main or virtual memory. Second, processor CPU register. Third is immediate, and lastly, input-output device. So later on in your section 4.4, you're going to play around with your addressing mode. Now we add some more. We know this is our opcode. We know this one is our source operand. But instead of knowing all of that, you need to know where you're going to fetch this information. This will be in your memory. You're going to store it into your memory, the thing that you are defined before your code here. Like total, normally you will going to like write total. Let's say 12H. There is byte here. So this, all the value that we declare above, we're going to store it into our memory. And this one, we're going to store in our register. Of course lah, this one is register. Of course, it's going to be stored in the register. And this is immediate value. This one is from input output. Read integer. So we call it from your input output. Last one is next instruction. Okay, this is loop. You can see we're going to loop here. Instruction representation. Each instruction is represented by sequence of bits that divided into fields corresponding to the constitutes elements of instruction. Example of simple instruction format: you have opcode, you have operand reference, you have operand reference, your source, your destinations, your source. So this is this very simple instruction in one line. Normally you have like move EAX, you have, let's say, the value of 2 lah. Then this is from a source to destinations, and also your opcode there. And here opcode are represented by the abbreviations called as mnemonics that indicate the operations. You can see this one we already learned it in previous, but I guess only this one, right? So load is new, store is also new, but of course you can like think about logic. Load is going to load from memory. Store, you're going to store the data to your memory. The rest, I guess this one you already know. No need for me to repeat anymore. So here is an example. When you have opcode here, of course you don't know what is 0001010 there. And from the program, this one is your machine language, I guess so. And this is the opcode. Instruction type, data transfer. You were given with the data transfer, said like that. And symbolic representation, you're going to have load MQMX. This is example, okay, what your programmer said. See, you are the one who program. So normally you will see like move EAX 1000 hash, let's say, okay. This is example. Or maybe you have MX addresses there. So it depends. So this is example of symbolic representations that programmer understand, but in terms of your computer, they just see on their opcode there 0001010. And on the description, your command, it is transfer content of the memory X located at X to the register of MQ. So during instruction execution, when you have a single line is read into a instruction IR in the processor. The processor must be able to extract the data from the various instruction field to perform the required operation. Okay, instruction type. What is your instruction type? Consists a high-level language instruction that could be expressed in a language such as example of C. So you're going to have total equal to total plus stuff. What was that? A single C instruction may require 3 machines instruction. This is typical of relationship between your high-level language and a machine language. So here is the example. You can see assembly language. First of all, you're going to load a register with the content of memory of your total there. Let's say I give you an example. When you have total, you declare first, right? Total in front, up. You're going to have like 100H, 100H, and you're going to load this value first. You're going to start, okay, this one, standby first, and then you're going to add with the content of your memory under your stuff, because stuff also you already declare to your register. Let's say it is like 50H, so you add, and after you execute this single line, this total will be stored back to your total. So the initial total is this one, which is 100H. After you execute this single line, this total will be updated to be 150H. Later on, if let's say you reload and reread these sentences again, the single line again, you can always like repeating, then you're going to update your total number, which is 200, and then repeat again, so if it is a load again. So this is what happened. Translating language, which is you have from this one is from English, of course. Total is assigned as the sum of total and stuff, and the higher language, which is equal to total total plus stuff. A statement in this one is in higher language, right? High level language instruction. So you can see one single line only, see there. But in your assembly, what you can do, I'm going to translate typical into several machines level instruction. This is your machine's code there. What your code sees from your assembly language. This is your higher level language from your C. But when you convert to assembly language, you can see that's why you have 1, 2, 3 line there. That's why it's much more slower rather than your one single line in your high level language. So under your instruction type, you're going to have 1, 2, 3, 4, which is data processing, the use for your arithmetic and logic instruction. For data storage, it's used for the movement of data in and out register, or even your memory. Data movement depending on your input-output instruction. And lastly, your control is for test and branch instruction. So this is all 4 type of instruction you need to know. Example on your first data processing here, of course you're going to play around with arithmetic and logic instruction. This is normal, like mathematical, the things that you already repeat several times. You can see the instruction and what is the function or descriptions in terms of arithmetic, and also a logical, which is normally you refer to your the things that you learn in your digital logics. Nearly to the same. So this is another example, see. And this is for your data storage and data movement here. This is data movement on the instruction. So you need to know the codes there, the opcode, and also the function and also description. And lastly, your control, which is test and branch, which is normally you're going to meet with the loop or even a jump. Something cool also. So that is the frequent use in our assembly language. Okay, Okay, next we're going to look into our number of addresses. One of a traditional way in describing processor architecture is using the number of addresses containing in each of instruction. If you give one instruction, how many number addresses contain? If two, if three. So what is the maximum number of addresses? It might be in any one of instructions. So mostly in one instruction, you're going to have one, two, or three operand addresses. Sometimes you even don't have any operand. I think last time also you already learned on this. Okay, program to execute. You were given this one. Okay, this is example, right? You were given with this like mathematical equation. So what you going to do? You're going to do the assembly language. In terms of maybe you can use one, maybe you can use two, maybe you can use three operand. So how many program that you're going to use in terms of if you use one operand, in terms of if you use two operand, and etc. So let me see the example here. If you are using 4 instruction here, you can see there is 1, 2, 3, 4 instruction, which is normally this one is your mathematical things, the things that you have here. This instruction is for A minus B. This instruction for D multiply with E. This instruction for okay, this one D multiplied with D, E, you're going to name it as T. So this T you're going to add with C, which is T plus C here, and here you name it as Y. And then you're going to update this to T, and then you have Y divide with T. At the final you're going to have a Y. So this is the things you can see in terms of 4 instruction. How many operand you have? You have how many addresses you have? You have 3 addresses. 1, 2, 3. And if you are using 2 addresses, how many line you need? You need more line compared to when you have 3 addresses. 1, 2, 1, 2. This is all 2 addresses. And 1 addresses you can see here. You're going to have 8 instruction. It's much longer. And lastly, sometimes you don't have any addresses, then you need 10 instruction there. How is it? So you can see the differentiation between each other, how you can construct your equation there to be your assembly language. And from this assembly language, how many operand that possible? You can have a lot. You can have 1, you can have 0, you can have 3, and etc. As long as you can see here, as long as you understand how the flow until you can represent the equation. Okay, now we're going to move to one by one. For 3 addresses instruction, for 2 addresses instruction, one addresses instruction, and lastly no addresses instruction. So how we going to look into? Okay, you can see here 3 addresses instruction. We have 1, 2, 3 there. You can see 3 addresses instruction. When we have 3 addresses instruction like operand 1, operand 2, and then this one is result or destination, this part, right? Operand 1, operand 2, we have a result. So this is addresses, 3 addresses, 1, 2, 3. You can see this you're going to sub, and you're going to store the sub here. Okay, so let me show you example. SUB, which is subtraction, you have y we have as a destination, and then you have another 2 as a source, but this one, this called as address, but you can see these two going to do the sub. A sub with 3, and then this answer will be stored to your destinations of y. That's why in your comment you can see y equal to A minus B there. Next, you can go through one by one. You can try copy this to your Microsoft Visual Studio and try to step by step look into what is happening. Okay, this is 2 addresses instruction. You're going to have destination and source only. One source, which is your operand, and another one is result, which is destination. A, you're going to put into your y. This one is you're going to put your sub there. You're going to have the destination of y. From y, you're going to divide with your b. And you can try to do all there. And one instruction is look like this. One addresses, implicate second addresses. You're going to use a CPU register, accumulates, supply one operands and store result. And lastly, a command on early machines. And for last example, for no addresses instruction, there is no addresses at all. All addresses are implicit. Usually use a stack, which is you're going to use a stack to push down a stack in your CPU. There are 2 opcode with 1 operand, which is push there. You can see push and pop, push and pop. Okay, now we're going to see how basically happen in our push and pop. We call it as last in first out, similar to your like a little Indian last module, I guess. So it's going to last input first out. So if you have any numbers, let's say you have 1, 2, 3, 4, 5, you're going to push 5 first. Let's say you push 5, right? 5, 4, 3, 2, 1. You're going to store it into your storage, let's say. First in, we're going to see first in. This is the first in, but it's called as last in. This is the last in. Last in is going to be first out. When you already like store it all, if you want to make it out, you're going to take 1 first, and then second, and then third, and then fourth, and then 5. It's called as LI4, last in first out. stack machines going to use a Java virtual machines. Call stack, a program also known as a function stack, execute stack, control stack, or simple simply the stack, simple the stack application reverse. Okay, this one. Under application, we're going to look into RPN, which is we're going to discuss later in the next example. And another one is deep first search. There is also a possibilities for you to look into the expression 3 here. You have A multiply with B. So how the expression 3 will look like? You're going to have like this A multiply with B. And then when you have another one, which is C, let's say, you need to remember on your mathematicals. So you're going to group this if it is a multiply here, right? So that's why you stick with this. And then when you have adding, you need to have 8 here. And then you're going to add with your C there. So it is one branch, but this is different branch because it is a next, which is this is prioritized, this is a second. Okay, although the C is in front, let's say you can see this is a mathematical, this is might be a, this will be the prioritized because this is multiply. If let's say you were given with the factorize there, of course you're going to do the factorize first. B plus C there in one branch, and you have another one is multiply with your A there. You can put also here it's similar things, and you can see you have several factorize there. You're going to do one by one. Maybe you can do this part first. You can see you put here, and inside this factorize you have this D minus E, and then you're going to multiply with your C there. So this is one group, and you're going to meet with this group with a multiplication. So this is the expression 3 you can use in terms of your mathematicals. If you have the equation of your mathematical, you're going to have the expression of your 3. Okay, this is another expression 3, but you're going to see later on you have infix notification, and another one is postfix notification. So you need to know both infix notification and also post notification. What is the difference? For infix, it's going to start with the left parent right. So this one is parent. Okay, later I show you, but you need to know it start with left parent right order, while for your post, left right parent. Okay, just now it is a left parent right, but now for post it's left right parent in order. Okay, you have here, we look into one by one in terms of expression 3 under infix notification. For our infix notifications, for left right parent, if we have this one, we're going to start with left. We have here on our left A and then we're going to have the parents of multiplication and then b. So this will be a roof of our uh, plus here. Left parent, this is left, we have a parent, and then there is a right there. Recursive left parent right again, we have left parent right, left parent right. Replace, recursive left parent right, we have infix of A multiply with B, replace sub 3 with the infix notifications. So this one, we're going to have the infix there. We're going to replace with the recursive left parent right, left parent right. Okay, now we look into post notification. For post notification, left right parent. We have what? Left right parent. We have example of this. Left right parents. What will happen? Just now we have left parent right, left parent right, left parent right. Now we have left right, and then we have parent there, and then we have left right parent. Okay, left right parents, left right parents. What is parent? Which is our operation there. So in terms of postfix, how we going to write? A, B multiply, and then we have C plus. Instead of just now we have like this, right? We have the similar tree. You can see the figure is similar. A multiply with B plus with C. But in terms of postfix notification, we're going to use left, right parents. Left, which is over here, is left, right parents. But for this one, you can see you have left parent right. From this tree, left parents right. And then we're going to move from this right, parents right. So left parents right, left parent right, left here parent right. So how we're going to use right? We're going to have A, B, and then we're going to have plus C. So it's basically like similar things, but this is one, and we have another C. So if you need to change from this to your infix, you're going to have similar thing, only that this will be one little child of roots for your plus there. And for postfix, although it is similar things, but in terms of postfix here, we're going to read from left right parents, left right parents. Okay, so reserve Polish notation. Reverse Polish notation here, we see the example we call as RPN, which is a postfix order. Let's say you were given with the infix. Okay, you're going to give with the infix. You need to represent in terms of expression. Let's see. We have what? For infix, we have left parent right. Left, we have here is our left parent and also our right. So we can come out with, don't look here first because you need to construct this expression tree. We have left parents, right. This is our left. We're going to have 1 plus 5. This is our left. And our parent now is multiplication. And this is all our right. So let's see this one first. We have 4 minus 1. And from here, we're going to have minus again with our 8. And okay, this is our 3. Okay, it's quite ugly. Basically, it's similar like this. Okay, so from here, when we have this expression 3, we have the infix to be our normal equation there. We need to change to postfix order because reverse our Polish notation. We're going to reverse where if we are given with infix, we need to come out with our postfix. It's going to be left, right, parents, isn't it? So you're going to meet you need to continue with your left. From here, what is your left? You're going to left, and then your right. Right, and then here will be left, right, and then you're going to meet your until your right. You can see again from left, left. This is another one child there. Left, right, parents. Finish this part. And then you're going to start with another one. Left, right, parents. Again, okay. You have this child there. You have another child. And you have these 3. You're going to solve this with your left, right, parents. And from here, you're going to continue with left, right, parents. Okay, so that's why you're going to have 1, 5 plus, continue with your left, another child 3 there, 8, 4, 1, minus, minus, and lastly, your upper, I can say that is like the key function there for you, a total parents for all. So this is your postfix. Postfix from your infix notification there. So from here, you have now is your RPN. Okay, how are you going to do this one? You can see you have 1 plus 5 multiply with 4 minus 1, 8 minus this child's that, and then you're going to multiply, right? So from here, you have the answer for this one is going to be a 6 there. And you solve this one by one, you're going to have 3, and then you're going to have 5, and you're going to multiply with 6 with 5, you're going to get 30. But in terms of your postfix order, how you're going to solve if you didn't see these 3? So in terms of postfix, you can solve like this. Starting from this part first, you're going to do 1, and then you have addition there. 1 plus 5, you're going to get 6. So you put there 6 first. And then from this 6, you have 6, 8. 6, 8, and then you have 6, 8, 4, 1, minus, minus, multiply. So from here, which is the one that you see the next operations? So the next expression is this one. You can see this is first operation. You have at this side is 1 plus 5. The second operation you have here, it will be 4 minus 1. So you're going to get 3. Where you're going to put? You're going to put here. And you can see there is another operation here. This is referred to the 2 digit there. 6 minus 3, you're going to have 5. You store at here first. And this will be 6 multiplied with 5. You're going to get 30. So you need to see and understanding the flow of this RPN. Okay, we need to have the evaluations of our RPN expressions on our infix and postfix. You can see this is the final answer, right? So you need to scan from left to the right until an operation is found. You can see, scan from the left to right. You can see, from the left to right until the operations, the things that I said just now. You can see operation is found, and the last two operand must be retrieved and combined. That's why you can see here, you scan from the left to the right, you found this operation, and last 2 digit here, you're going to combine and do the operations. After that, you're going to store here, right? And you can see you scan again. Scan left to the right until you meet the next operand, and last 2 digit here, you're going to combine to do this, and so on. So this is instructions. Okay. And all the things here you're going to store later on in terms of LIPO. Last time, you still remember what is LIPO? Last in, first out. Okay, evaluate the RPN expression flowchart. So you can see basically how is flow. Please try to check it. Okay, now in terms of stack. Okay, how you going to store inside your stack? In terms of this. Okay, what happened is, first you're going to store the 1 there. You're going to push. Okay, you're going to push. You scan, you're going to push this 1 inside, and you can see you find another numbers, you're going to push inside also. Then after that, you scan, oh, you have operand. So you're going, if you found the operation, you're going to pull. You're going to pull. So what you're going to have here, not pull, okay, push, pop. So you're going to pop or also pull. That's why you're going to have 1 plus 5 equal to 6. When you have here, you're going to store back. Store back. You can see, you store back, you push back to your stack. You're going to store back to your stack over there. And evaluate the okay. And then after you have this, you scan again. You have 6, right? This one. So you scan, you have 8, you're going to push inside. You have 4, you push inside. You're going to have 1, you push also inside there. You see? So this is your stack, what is happening. And when next time you meet your operation, what you're going to do, you're going to pop it out. Pop it out. You're going to have 4 minus 3. When you pop is already, then you have left this one only. This answer you're going to push back into your stack there. Okay, now you can see there. When you have here, you're going to scan again. After this, you're going to meet with operation. That's why you're going to pop again. 8 minus 3. You're going to pop, and you have the value of, let's see, okay, you pop here, you have the value of 5, you push back inside your stack. Then you scan again, you're going to meet with your multiplication. That's why you're going to pop. When you meet the operation, you're going to pop. Then your final answer will be totals of, you push from your multiplication there. So only one value on the stack, and this is the final result when there is no more operations that you need to do. Okay, here is example when you were given with this expression, how you're going to construct the expression 3, convert into PRN post-fit evaluations. So let's see how it goes by there. You can try to do first. Maybe in class we're going to discuss together. Same goes to the exercise 4.1, or maybe later on I'm going to see. I'm going to create one by one the video for each of the exercise there. And let's see. Okay, we're going to finish our 4.2 first. Then I'm going to stop and continue with another video because it's too long now. How many addresses, numbers of addresses per instruction is based on design decisions. So more complex instruction, if you have more addresses, fewer instruction per program, more register are needed, which is much more quicker. Fewer addresses is less complex, fast in a fetch and executes, and more instruction per program. On the instruction set design, the design of instruction set is very complex because it affects many aspects of our computer system. So the instruction set define many of the functions performed by the processor. The instruction set is the program's means of the controlling the processor. Those the programmer requirement must be considered in the design of instruction. So this is the fundamental things, the things that you need to understand in terms of the design issues on the operation, on the address, register, instruction format, and data type. Before you can move around, hope that you can understand all of this. So I guess only until here for our video for this. Later we're going to continue with our 4.3, 4.4, 4.5. But this one is not too critical if you already understand our machine instructions. Okay. So thank you for your watching. Meet again in our next video. Bye.